So yes, we have talked about the production of sound. So vibration was necessary to produce the sound. We also talked about propagation of sound. In order for the sound to propagate through a medium, there should be the particles in the medium, and these particles in the medium will vibrate because of the disturbance created. So disturbance, that means the source which is producing the sound, that source is also important. The medium is important for the sound to travel or propagate. And finally we come to the last end which we will discuss today, that is once the sound reaches the listener, somewhere you will see that it is mentioned as observer. So
Yeah.
once the sound reaches the listener's ear, then how the sound waves are interpreted, we will discuss that today. So basically we will see that with respect to human ear. We know
Okay,
ear
but
is part of
should it?
human body which enables us to hear. We will talk about what all parts are there within the ear, the complete structure of the ear we will see. Okay,
What
but
about
before that let us
reflection?
have a brief idea about
Hello.
the reflection of sound. Right, this will be the end thing which we will go through. So we are in the medium now. In the medium, what may be possible? There may be reflection of sound, or some sound waves could be absorbed. So we will talk about the medium quite more, what all possibilities could take place. So first thing is reflection of sound, and this is a very simple thing. Reflection, we have the idea that is described as the bouncing back of ray of light. Bouncing back of ray of light. So in terms of light, we have seen that if you have, let us say this is a mirror, if you incident a ray, then that ray will be bounced back such that it makes equal angles with respect to the normal. That means this I
Yeah.
will be equal to this R. We call this
Yeah.
I as angle of incidence, and this R as angle
Angle
of
of reflection.
reflection.
Yeah.
So this surface over which the reflection is taking place, that is definitely called as the reflecting surface. Okay, so this we saw with respect to a light. So bouncing back of ray of light. So okay, we will not describe in terms of ray of light. We can also describe reflection as the bouncing back of sound such that it makes equal angles. So how this experiment is verified? Let us say we have a table, and let us say this is the wall. So we use two pipes here. Let us say this is one pipe, and you keep an alarm clock here. Let this alarm clock ring, and take another pipe. So you have to fix this pipe, and this pipe too can be movable so that you can move it here or here along these directions, A or B. So you will get a particular direction at which you can hear the sound. If you put your ear here, you can hear the sound, and that is only possible when this I is equal to this R. Right, so in sound also,
Yeah.
where the reflection of sound takes place, this law of reflection holds. This I is equal to R, what it is? It is the law of reflection. Okay, so we are confirmed that sound has the tendency to reflect. So due to this reflection of sound, there is a phenomena called the echo of sound that takes place due to reflection of sound. So you might have observed that once we enter an empty room, in an empty room, if we speak something, then we are able to hear our own echo. Whereas
Yeah.
in the room which is filled with items, or you can say things, so room which is occupied or filled, there you will observe there is no echo taking place. So here the echo takes place. Now what is the reason for this echo taking place? The reflection of sound through the walls. So whatever we are speaking, that sound wave hits the wall and returns back. So reflection of sound with respect to wall, That is the reason for the echo taking place in the empty room. Whereas in the room filled with things or items, there is no echo taking place because there is no reflection of sound. So if there is no reflection of sound, what happens to the sound waves that we produce? That gets absorbed. So here we will remember, sound gets absorbed by the objects present in the room or items present in the room, right? So before hitting the wall, the sound waves are getting absorbed before hitting the wall, right? You will observe that when there are less item considerably, then you will hear somewhat echo. But if the room is completely occupied with the items or things, we will definitely not hear any sort of echo. Okay, so this is a simple phenomena of reflection of sound. Now there is possibility that reflection of sound can be multiple times. So we call that as multiple reflection of sound. So due to this multiple reflection of sound, the sound reverberates. So what is the meaning of reverberation? We will see. So let us suppose a sound is created in some big hall. There is a very large hall and sound is created in that large hall, and this created sound, it hits the walls consistently, and due to that multiple reflection of sound takes place. So the repeated reflection, there might be possibility that if let us suppose the hall is like this, so sound wave is coming here, it is hitting, it is reflected, again it is reflected. So we can see there are multiple reflections of sound taking place at these places. So due to this multiple reflection of sound, the sound reverberates or the sound persists. So this persistence of sound waves due to multiple reflection, that is called as reverberation. So let us go back to the reflection once again. Let us suppose from here sound is created. Let's say this is the source and this is a wall, and the sound wave is hitting the wall and it is getting reflected. So it is reaching the source. Let us suppose I am only creating the sound. So sound wave is reaching again back to my ears. So I can hear my own sound. What is echo? If you have to define, we can say echo is the phenomena of hearing sound created by source, right? I have created the sound and I am able to hear my own sound. And so here what happens, let us suppose sound travels with some speed in the medium. Let us say the speed of sound is v. Let us say I can measure the time taken by the sound to hit the wall and reach back. So this t, what is this t? T is the total time taken to go from source to the wall and back from wall to the source. Now here, if let us suppose source and the wall are placed at a distance x, then we can relate x, t and v. The equation will be distance is equal to speed into time. So what time I have to take? I have to take t by 2 time, because t is the total time taken to loop from source to wall and back to the source. And x is the distance traveled by sound in time t by 2. So I can get x is equal to v into t by 2. So this thing we will keep in mind. In the question we will especially focus on whether the time given is for the complete loop, or some question may also contain the time taken to go from source to the wall. Okay, so here we will remember an important result. Very important result, that at least the source should be 17.5 meters from the wall. So somewhere you can see 17 meters, that's also right. So approximately it should be minimum 17 meters from the wall for the echo to
Yeah,
hear,
why is that?
for the echo to take place, we can say.
Okay.
That means we can also find out the minimum time which is required for the echo. So let us find the minimum time. We have the distance, and normally the speed of sound in air, that is approximately 330, although it changes depending on various factors like the density, depending on humidity, but let us consider because we are finding approximate result. So speed is this, distance is 17 meters. Okay, I'll do one thing, I'll take the speed as 340. Approximately it goes from 330 to 343. So
Yeah.
340 I'll take. I can find the time as distance by speed. So 17 by 340. So that comes out to be 1 by 20, and that is 0.05 seconds.
Okay.
Right? So what should be the
Yeah.
total time taken for the sound to hear the echo? Answer in that case will be whatever answer we got, we have to multiply that with 2. Right? Because we have just found the time taken to cover 17 meters or to go from source to wall. So in that case it will be 0.1 seconds. 0.1
Yeah.
second is the minimum value for t. If the sound is going from source to wall and coming back to the source in less than 0.1 seconds, there will no echo take place. Okay, so moving ahead now. So there are certain applications for this reflection of sound. If I want to increase the range of hearing, then I can use the concept of reflection of sound. So you would see that some of the conference hall, they have curved ceiling. So let us see why they have curved ceiling. So let us say here we have source and the people are sitting here in the rows. So if the source will speak something, definitely the sound will go and hit the eardrums of person 1, person 2, and in this case the sound will get absorbed. So for that purpose what we have, a curved ceiling. So the curved ceiling, what it will do, sound will travel in all directions, so it is able to reflect and increase the range, so that this part of energy is only absorbed by this person. Some sound waves will also be reflected like this because sound travels in all directions. So in this case, in this manner it will be able to reach even the listeners who are at the extreme end. So this is a generally good idea to have a curved ceiling in a big conference hall, not normal one, in a big conference hall. It's a good idea to increase the range, which will increase the intensity of the sound heard by different people. Okay,
Okay.
there is also one more application that is similar to this application which we learnt. So if we talk about a big hall again, or let us say an auditorium, there generally it's a good idea, although you will not find this at many places, at all the places, but it's a good idea that the back of the wall, let us say this is the stage, and the back of the wall, if it is curved, not too curved, even though if it is very less curved, what will happen, the source which is creating the sound, in this case, that is correct, some sound waves will travel in this direction, but sound waves will also travel equally in this direction. So what will happen, they will get reflected, and as a result the sound intensity propagating to the right can be increased. Earlier you can see, let us suppose only half part of sound was going, but now even the other half we are able to send in this direction. So we have increased the intensity. Intensity was related to the energy, and more
Yeah.
the energy a sound is carrying, more tendency it has to go or travel to the larger distances. Like if we increase our sound or we scream with louder voice, all the people around us can here, because the range of sound is very high, because I am investing a lot of energy to create the disturbance in the surrounding. Okay, so here it has increased the intensity of sound.
Yeah.
So let us do some questions based on whatever we learned related to the reflection of sound, including the multiple reflections.
Okay.
So let us do this question. A person clapped his hands near a cliff and heard the echo after 2 seconds. What is the distance of the cliff from the person if the speed of sound taken is 346 meter per second? This is the time taken to hear the echo is given as 2 seconds. So we will take the time taken to travel x distance. X is the distance between person and the cliff. So time will be half of this total time. So 1 second, and yes, speed is 346. Very simple. We'll use distance as speed into time. So that will be 346 meters. Okay, another one. So let us suppose an echo is heard in 3 seconds. What is the distance? What is the distance of reflecting surface from the source? Given that you have the speed of sound, 342 meters per second. We can see with respect to questions, the speeds are mentioned because as we know, speed varies and roughly it lies around 330 to 345, 46, around that. So again, we can see the same idea. It is the time taken to hear the echo. So what time we will take to find the distance of the reflecting surface from the source? Source is here, reflecting surface is here, and let us say the distance between them is x, and I can find x using distance is equal to speed into time. Speed is 342 and time is 1.5. So I can moreover do it 342 into 3 by 2. So that will be 171 into 3. That will be, yes, 513 meters. So now we will see the next topic, that is the speed of sound in different medium. So that will be the first thing we will see, and we will also see the speed of sound depending on various parameters with respect to various factors. So factors here can be temperature. That means if I increase temperature, will the sound propagate more? Based on
Okay.
humidity, because these are the only two factors around us which are continuously changing. So talking
Yeah.
about the speed of sound in different medium. Medium means I am talking about the different states in solids, liquids, and in gases. So as we know that propagation of sound is a function of the particles in the medium. So in these three states we see that in the solid state the particles are very closely packed, and as a result the sound propagation will be more, or you can say the sound travels at high speed. So if I arrange the speed of
Yeah.
sound propagating in these three types of medium, in sound it will be maximum and least will be in gases, because here the particles are very far apart, whereas in liquids the particles are intermediately spaced. So it has less separation with respect to solids, but obviously more separation with respect to gases. So in short, here particle density in solid, that is more. So if particle density is more in solids, means that the particles will be able to transfer the energy more easily. It need not go and travel a larger distance to give its energy or supply its energy to adjacent particles. Whereas in the gases, the speed of sound will be very low. Talking about the factors, it is very indicative that the factor which is able to increase the rate of transfer of energy, because we saw sound as a form of energy. So those factors which are able to increase the rate of transfer of energy, rate means the speed of transfer of energy, then in that case the speed of sound will be more. So if I increase the temperature, what is likely to happen? Will the speed of sound increase, or will the speed of sound? If I am increasing the temperature, the vibration of the particles are increasing because they are getting more and more energized. So if they are getting more and more energized, if they are able to vibrate more, so they will transfer the energy easily. So if I increase temperature, remember, the speed of sound increases. In the same manner, if we increase the humidity, that means we are increasing the liquid content in the atmosphere. So it is just like gaseous state is somewhat approaching to the liquid state, or you can say humidity means more water molecules present in the surrounding. As a result, water molecules, they are also acting as particles. So particle density has increased, and in this case also speed is likely to be increased. So a normal question comes. Let us suppose in a rainy day and during a hot weather, during which season we expect the speed of sound to be more, and the answer is rainy day.
Yeah.
So why the speed of sound is more in on rainy days? Because
There's much more
of higher humidity,
water content
because
in
of
the
more
atmosphere.
particle
Yeah.
density. Okay, so the next thing we are going to see is the range of hearing. So different organisms, they have different range of hearing, and we are only interested as of this point to go through the range of hearing with respect to human ear. So it is true that humans, or we cannot hear all the sound around us. We can only hear those sound whose frequency is between 20 hertz to 20 kilohertz or 20,000 hertz. Right? We can hear
Yeah.
sound whose frequency lies between 20 hertz to 20,000 hertz. And this set of frequency, we call this as the audible range. So it is only the audible range of human ears. So if any sound, let us suppose I have a source which is producing 10 hertz sound, or sound with frequency 10 hertz, then definitely our ear cannot respond to this. We cannot understand or hear this itself, because this frequency is not lying in the audible range. So here you can see the sound in the audible range. 20 hertz is the frequency of the sound wave. It is the minimum frequency of the sound wave which our human ear can hear. So that is called as infrasound. So infrasound, sound with frequency even less than this minimum frequency in the audible range. Infrasound, you can say sound with frequency less than 20 hertz. On the contrary, we have ultrasound. These are the sounds with frequency greater than 20 kilohertz or 20,000 hertz. So this concept of infrasound and ultrasound, that must be remembered. And along with this, it is also important to remember that this ultrasound, since it is having very high frequency, right, very high frequency, we also call it as VHF sound, means very high frequency. So since this sound is having very high frequency, it is likely to have or contain more energy. High frequency means more energy, contain more energy. So if it has more energy, that means if the sound wave, if ultrasound is traveling a larger distance, there is less chance that energy can be completely lost, right? Let us suppose I want
Yeah.
to, here I want to use the phenomena of echo to find or to calculate some distances. Definitely this involves reflection of sound. So which sound I will prefer? Definitely the ultrasound, because it will hit and it will have definitely the tendency to return because its range is very high. Why its range is very high? Because it has more
High
energy which
frequency.
cannot be completely lost. Okay,
Yeah.
so these ultrasounds, these are used in sonar. Now this is a device which is used to detect the depth of sea. Not
Oh,
only it
okay.
is used to detect depth of sea, but also it is used to detect the location of targets. Targets, I mean, let us suppose there are two ships in the ocean. So let us say this is one ship, and let us say some ship is coming here to completely destroy ship 1. Then in this case, how this ship 1 can analyze whether any target is present nearby? It can emit ultrasound. So if that ultrasound is able to reach back to ship 1, then it will understand that there is some target from where this sound has reflected, right? So this sonar, what actually it has? Sonar has a transmitter. Sonar has a transmitter, as well as it has a detector.
Okay.
So what will sonar do as a whole? Let us say it is present in some ship. Sonar will emit ultrasound waves, right? Many ultrasound waves, and as a result, these ultrasounds will reflect back. So if it will reflect back, it will reach the detector. So detector can sense whether it is the same ultrasound which is emitted. So this detector is designed such that it will detect only the ultrasound sent by this transmitter, because there might be
Oh,
possibility some other ship is sending ultrasound, so it will not detect
oh,
that. It will set
okay.
its own frequency range and it will check whether the received frequency is within the same frequency range. So once it is able to detect, it will record the time taken for the ultrasound to be emitted from transmitter, reflected, and reaching back. The complete time taken for this loop will be calculated, and again we will find the depth of sea, let us suppose, using speed of sound into t by 2 approximately, right? Because you will say, we will say that this is the distance which is traveled and how we are getting this distance. So this is an approximate one, because the separation between transmitter and detector is not this much. It is like transmitter is here, detector is here, and the distance is very large. So approximately this seems to be a straight line, right? This seems to be a straight line. So we calculate approximate distance using v into t by 2.
Okay.
So these ultrasounds, these are not only emitted by sonar, but almost all the organisms who live within the sea or in water, in aquatic lives, whoever organisms or plant, whoever is there, they emit ultrasound to catch the prey. Even if we talk about bats, what do these bats do? They emit ultrasounds, and if these ultrasounds hits an insect, then this ultrasound is reflected back. So once this bat is able to receive that, once this bat is able to understand that this is the same ultrasound which I have emitted, then it will understand that the prey is here, the insect is here. So bats will move in this direction. So bats continuously keep on emitting ultrasound, very high frequency sound. So we can see the applications of ultrasound. What are the applications of ultrasound? It can be used to detect the depth of the sea, to detect the location of the targets. Even it is used by the bats to catch their prey. So number 3, used by
medical professionals.
bats to catch the prey. Even if we talk about the fish, let us suppose this is the surface of water and the fish is moving here in this direction. So in this case, this fish will emit ultrasound, and as a result, if something comes on its way, it will turn, because it will understand that I should not go in this direction. Okay, these were the applications. Yet we have another application, and in fact a very important application. So let us suppose I extracted some element from the earth's crust and I have constructed a metal rod. Let us say this is a metal rod which I have to use for making the rails on which the trains can go. So definitely I want this not to be faulty. So for that purpose I have to inspect that if there is any holes or any cracks or any crevices here. So to check for the cracks or crevices, we use ultrasound. So how it is used, let us check that. So let us say this is the metal piece which I have to detect. So what we do here, this is a source. So source of ultrasound. So this source of ultrasound, it will emit the sounds, and wherever the crack is present, sound will be reflected from that crack. Sound will be reflected from that crack, and here we add the detector. So this detector will be able to sense the complete, on its complete surface, detector will be able to sense the sound which is emitted from the source. But only in this region the sound will not be detected. That means we will be sure that there is some crack or crevices in this region. So crack, if the crack is present, we have to remember, in case of, or if the crack or crevices is present, then the ultrasound is reflected back. So now the question arises, why it is reflected back if the crack is present? Because definitely the crack will be uneven, and if the surface is uneven, then reflection is very much significant.
Yeah.
So there are multiple applications, other applications of ultrasound, like even in medical industry it is used for the operations, for multiple medical surgeries it is used, because through this we are able to understand that which part is defective or where the ultrasound is not reaching, then that can be a faulty region, right? It can be even used to get the complete imaging of internal organs of human body. So if this is understood, then now let us go through a simple question based on the application of ultrasound in the sonar. So let us do this one. A ship sends out ultrasound that returns from the seabed and is detected after 3.2 seconds. So let us say this is seabed and this is the ship. So a sound is sent and it is returned back in
Mm.
3.42 seconds. If the speed of ultrasound underwater, the speed is 1531 meters per second, then we have to find the distance of the seabed from the ship. So this distance we have to find. That means basically we have to figure out the depth of
Yeah.
sea.
Okay. Just
So one thing must be made sure, that we are not going to use this time, we are going to use half of this time, 3.42
yeah.
by 2. So distance will be speed into that halved time. So that will be 1531 times 3.42. That will be 2.68 kilometers, or whatever answer we'll get, that will be 2680 meters. Let us do this one. Submarine here emits a sonar pulse which returns underwater cliff in 1.02 seconds. If the speed of sound in salt water is 1531 meter per second, how far away is the cliff? That means somewhere there is submarine, and this is underwater. So there is some cliff over here, and the submarine sends signal which is able to hit the cliff and return back in 1.02 seconds. So definitely we are going to take the time as half of this. So it will be 0.51 seconds. And the
Hello.
speed of sound
Yeah,
is
I
given
got.
in salt water, that is 1531 meter per second. And we have to find out
Yeah, I got.
how far is the cliff from the submarine. That means the distance between them. So let's say it is x.
Yeah.
So it will be speed
Hello.
into the time, 0.51 meters. This comes out to be 780.81. Okay, so the last thing that is left now, we will go through that. That is the structure of human ear. So we will have complete idea about the structure of human ear. This generally comes as a 5-mark question. You have to draw, and with respect to the diagram you have to explain the proper functioning of human ear. So definitely
Yeah.
this indicates that we have reached at the observer or the listener side.
Yeah.
So we have talked about production of sound, propagation of sound, and now we are at the observer level. So here in the human ear, we can see that the sound coming from the source propagating through the medium is collected by the pinna. So I will write the exact functioning of each of these parts. So pinna, what it does, it collects all sound waves. So pinna collects all sound waves. And now this portion, you can see this is outer ear, middle ear, and then inner ear. So main parts we have
Yeah.
in the middle ear that we will focus. So outer ear, here we have the pinna, and that collects sound, complete sound which is available in the surrounding, it will collect. And this collected sound, it will pass through, we can see, the auditory canal. So auditory canal, what it does, through this collected sound
It's the passage.
passes. Okay, and at the end of this auditory canal, at the end of this auditory canal, we have eardrum.
Yeah.
Right, we have eardrum. We can see, we also, this other name also must be remembered, this is
Yeah.
tympanic membrane
Tympanic
or
membrane.
eardrum. So collected sound at the end, at the end of, I'll write AC to indicate auditory canal.
Yeah.
At the end of auditory canal, the sound wave hits the eardrum. Sound hits
Yeah, and starts
eardrum.
vibrating.
So eardrum, as the name suggests here, tympanic membrane, this is a very light, very thin membrane, and
Yeah.
we know the sound propagates in the form of successive compressions and rarefactions. There is
Yeah.
successive compressions and rarefactions. So using this idea, we can understand that when compression reaches the eardrum, then the eardrum goes in, because this compression is carrying more particles. That means more energy is present in that, at that point. And when the rarefaction will reach the eardrum, then the eardrum will relax and come back. So as a result of successive compressions and rarefactions hitting the eardrum, there will be vibration of eardrum, right? We agree with this?
Yeah.
There will
Yeah.
be vibration of eardrum, right? So this compressions and rarefactions, due to this there will be vibration, and the eardrum, definitely it will vibrate or oscillate, whatever we say, both are same. And now these vibrations which is produced by the tympanic membrane, they are generally energized, or you can say in more scientific form, they are amplified by the three bones So after the tympanic membrane, the vibration is amplified by the three bone. What are the three bone? Hammer, anvil, and stirrup.
Hello.
What they do?
Last.
They amplify
Hello. Hello.
vibration
Hello.
produced by
Hello.
the eardrum.
Yeah. Hello. Hello.
So basically this,
Hello.
now it has reached the middle ear. Everything is now taking place in the middle ear. And then what happens? Once it has amplified, now it will let the amplified signal or amplified sound travel to the inner ear. And these amplified sound waves, right, still till now it is amplified sound signals only or sound waves only. So they are converted to the electrical signals, and this conversion is carried out by a component cochlea, right? So what does cochlea do, which is present in the inner ear? It will
Converts
convert
the sound waves.
sound wave into electrical signals. Why it will convert sound waves into electrical signals?
So that
Because
the brain
the
can comprehend the sound.
brain can interpret only electrical signals, right? Brain cannot understand sound signals, and it does not make any
Yeah.
sense to send the vibration into the brain. So brain can interpret only electrical signals, and that's why the sound waves which are amplified by many times by these three bones, hammer, anvil, and stirrup, they are converted to electrical signals by the cochlea. And then these electrical signals, whatever is converted here, these electrical signals that will reach to the brain via this
The
auditory nerve.
auditory nerve.
So
Yeah.
we will not get confused with this auditory canal and auditory nerve. So what does auditory nerve do? It sends
It transmits the
the
signals.
electrical signals to the brain. So we can write here auditory nerve, not the auditory canal. Auditory canal is in the outer ear only. So auditory nerve, it will send the electrical signals to the brain, and once the electrical signal is received by the brain, it will be interpreted as a sound, and we will be able to understand the complete sound which is collected by the pinna. So overall we can see here the sound collected by pinna. We can draw the flow here. Sound is collected by pinna, and what this pinna do now, it will allow the sound to pass through to the inner ear. Before that it will be in the middle portion. So the collected sound will now pass through auditory canal. So sound passes, and then what it does, it hits the eardrum. We also have another name for eardrum. What was that? Tympanic membrane. So it hits the eardrum, and once it hits the eardrum, it vibrates, and after the vibration, what happens? These vibrations are amplified. So these vibrations are amplified. So who amplifies these vibrations? The three bone-like structures. They are hammer, anvil, and stirrup. Has hammer, anvil, and stirrup. So what happens now? These amplified signals are now converted into electrical signals. So who does this conversion? Cochlea.
The cochlea.
And after this conversion, what happens? After this conversion,
The electric
these electrical signals are sent to the brain via auditory nerve. So these nerve endings will send the sound waves to the brain, and it will now interpret the sound waves. So it interprets sound. So by this we have completed full sound chapter. Okay, so we have completed all about the human ears, and yes, if you all have not gone through the first part of this sound, so I'll post that in the description box. You all can check them, and yes, see you all in the next lecture.